All right, here we go. Question 23 from our pre-calculus, homework 13. In MyLab Math, we have another mathematical induction problem. So if we read on, it says the first condition that the given statement must satisfy in proving that it is true for all natural numbers n is that this statement is true for, and that's got to be 1. The first condition is always proving that it is true for the first term of the sequence. Okay, next for part 2, complete the steps to show that the statement is true for the appropriate value of n. So we're going to have to show that it's true for n equals 1. And so if we scroll down to where we can see everything here, notice that n plus 2, the n got replaced with a 1, so every n gets replaced with a 1. So 1 plus 3, 1 up top, 1 here. That just shows that you're plugging in a 1 for every n to calculate the first term of the expression. Okay, so the next step is to show that the left-hand side does indeed equal the right-hand side. Notice our first term was 1 over 3 times 4, and this will simplify to 1 over 3 times 4, and I believe we do need to calculate that value. So as a value, that would be 1 over 12. 3 times 4 is 12. On the right-hand side, notice that this expression will also simplify to 1 over 3 times 4. And again, I believe we need to input that simplified, 1 over 12. And next, we're already to part 4. What is the second condition that the given statement must satisfy to prove that it is true for all natural numbers? Well, remember the first statement says that it must be true for when n is 1. Next, according to our theorem for mathematical induction, we need to assume that it's true for k and then prove that it's true for k plus 1. So if the statement is true for some natural number k, it must also be true for the next natural number. That is the actual statement for the second condition. Part 5. Write the given statement for k plus 1. So we're going to input the fraction, but now we're going to replace every k with k plus 1. So that's going to be 1 over, parentheses, k plus 1 plus 2 would be k plus 3 if I CLT, and then multiplied by k plus 1 plus 3, which would be k plus 4, again if I CLT. And on the other side, we need to plug into our formula on the right-hand side, replacing every n with k plus 1. So that would be k plus 1 over 3 times k plus 1 plus 3, which would simplify to k plus 4. So here we go. As a fraction, clicking the fraction button, that would be k plus 1 all over 3 times, we said k plus 4 simplified. Next, part 6. Now, according to the principle of mathematical induction, assume that our statement is true for k. So that's where we need to input this fraction, which is our formula, but replacing the n's with k. So that would be k over 3 times k plus 3. Part 7. Use this assumption to rewrite the left side of the statement for k plus 1. What is the resulting expression? All right, so this is where it gets a little bit sticky. So I thought I should come over here to the scratch work and try to help it make sense for you. So here is our statement. We assume that this is true for when n is k. So we know that the sum of this expression to the kth term will be equal to k over 3 times k plus 3. So do you see what we can say is that the sum of this expression out to where n is k can be represented as k over 3 times k plus 3. And then in order to show that it's true for the k plus 1 term, for the next term of the sequence, what we would do is we would add to both sides the next term of the sequence. All right, so hang tight. Showing adding the next term of the sequence, we would say plus 1 over, and now we're going to increment k, which would make that k plus 1. So we would have k plus 1 plus 2 times, again, k increments, k plus 1 plus 3. And this would be the next term in the sequence, but whatever I add to one side, I have to add to the other. So I would add on the other side 1 over, and then I'm going to simplify. K plus 1 plus 2 would be k plus 3 times k plus 1 plus 3 would be k plus 4. So we would have to add this to both sides. And then that would give us k over 3 times k plus 3. That would be the sum of the first k terms, and then plus the next term, which would be 1 over k plus 3 times k plus 4. So I believe this is what they want when they say rewrite the left-hand side of the statement for k plus 1. All right, so back in our MyLab Math window, I have input what I think is the expression they want us to show. And that is what they wanted. Next, part 8. What can be done to show that the resulting statement for k plus 1 is true? Well, I think we need to go to our scratch work and actually do the work and then see which statement applies. So from our previous step, what we just calculated was that the left-hand side of this expression can be written like this. For the sum of the k plus 1 terms, what we want to show is that this is equal to the formula if we replace every n with k plus 1. So that would say k plus 1 over 3 times k plus 1 plus 3 would simplify to k plus 4. So now we want to show mathematically that the left-hand side equals the right-hand side. So how do we need to do that? What I recommend is that we follow the same strategy as when we do our trigonometric proofs, proving a trigonometric identity. Normally what you're taught is that you work on the more complicated side to get it to simplify to the other side. So what we're going to do is we're going to work on the left-hand side and see if we can get it to simplify to the right-hand side. In order to add those two fractions, we're going to need a common denominator. So notice that the fraction on the left, the 3 times k plus 3, he needs the factor of k plus 4. And so I'm going to multiply him by k plus 4. Whatever I do to the bottom, I have to do to the top. And then on the second fraction, he's going to need the 3 that the first one has. So I'll multiply his numerator by 3. And then once we have a common denominator, we can say 3k plus 3 times k plus 4 is our common denominator. And then we can add the numerators. Doing the distributive property, that's going to give us k squared plus 4k plus 3 And again, what we're trying to get to is this fraction right here. So the next step is to notice that our numerator is a standard trinomial. Let's see if we can factor that. So factoring the standard trinomial, the signs are both going to be plus k and k to make k squared. Numbers that multiply to make 3 and add to make 4, 3 and 1, all over the LCD. 3 times k plus 3, k plus 4. And then will this rational expression reduce? Yes, it will. We can cancel the common factor of k plus 3, giving us k plus 1 over 3 times k plus 4. And then if you look at where we're at, this fraction is identical to the fraction we were trying to get to. So that is the process mathematically that you go through to prove the statement is true for k plus 1. Now what did we do? We got a common denominator, we simplified the numerator, and then we reduced the fraction. So now let's go back to the MyLab Math and see if that was similar to one of the options. All right, so back at our MyLab Math, we just showed what could be done to prove the result is true for k plus 1. And if you read part B, what we did is we wrote the terms of the expression on the left-hand side over a common denominator. Oh, and we did factor the numerator, and then we divided out the common factor to make the expression equal to what was on the right-hand side. So that is what we did. And then it looks like for part 9, there is actually nothing to do. See, I've already gotten credit for that. It just basically states for part 9, since both conditions of the principle of mathematical conduction are satisfied, then we have shown that the given statement is true for all natural numbers. And so that's going to do it for that problem. If you have any questions or comments about anything covered in this video, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.